In this section, we'll cover some of the basics of probability. Probability helps us analyze and make sense of data to help us determine how likely an event is to occur. From helping with weather predictions to the chance someone would win the lottery, probability can help us in the world we live in. Let's start with the basics of probability. The probability of an event occurring is the chance or likelihood of that event occurring expressed as a percent, decimal, or fraction. An event that is certain to occur has a probability of 100% or 1. An event that cannot occur has a probability of 0% or 0. So this means the largest you can get for probability is 100% or 1, and the smallest is 0% or 0. There's different types of probabilities. We've already used, when we learned about contingency tables, we were doing what's called empirical probabilities. Those are based on observations or experiments, so like surveys that get conducted. And then there's theoretical probabilities. So those are based on the assumption that all outcomes are equally likely. In this section, we're going to focus on theoretical probabilities, but let's first make sure we can tell the difference between empirical and theoretical. So which type of probability, empirical or theoretical, is being described in the following situations? Based on geological evidence, the probability of a major earthquake happening in Oregon in the next 50 years is 20%. So this is based on observations. So we would say this is empirical. The probability of tossing a coin and getting a heads is 50%. So they're not saying I tossed a coin 50 times and got heads 50% of the time. Instead, this is just saying the probability is that because it's equally likely that you get a tails or heads. This is a theoretical probability. So let's continue with theoretical probability. Theoretical probabilities are related to situations in which each outcome of an experiment has the same chance of happening, as we said earlier. So the result of an experiment or observation is called an outcome. And a particular outcome that you're interested in is called an event. The sample space is the set of all possible outcomes. So let's look at sample space. Determine the sample space of the following. Rolling a 6-sided die. So what are all of the possible outcomes I could get? We're going to use set notation to denote this. And typically we usually use like a capital letter sometimes to denote the set. So our sample space is, all right, all the possible outcomes when you roll a 6-sided die. You could get a 1, get a 2, a 3, a 4, a 5, or a 6. What's the sample space for tossing a coin? Well, what are the different options I could get when I toss a coin? A heads or a tails. A sample space of pulling 1 marble out of a bag with 6 red marbles and 2 blue marbles. So what are the possible outcomes when I pick a marble out of the bag? I could pick a red marble or I could pick a blue marble. So I'm not writing red 6 times. I'm just saying, again, your sample space is all the possible outcomes. So I could get, when I pick out a marble, it'll either be red or it'll be blue. Tossing 2 coins. So the sample space for that, all right, when I toss 2 coins, I could have both coins have heads. So I'd write heads, heads. I could have the first coin be a heads and the second coin be a tails. I could have the first coin be a tails and the second coin be a heads. Or I could have both of them be tails. So that would be the sample space for tossing 2 coins. When the outcomes of an experiment are equally likely, the probability of an event A is expressed as P of A is calculated by dividing the number of ways that the event can occur by the total number of possible outcomes. So for example, the number of ways that we'll call an event A, so this would be P of A is how we notate this, divided by the total number of outcomes. All right, so let's answer the following. Let's look at an example of this. What is the probability of rolling a 5 with a 6-sided die? All right, so again, I always write out the sample space for this. So if I'm rolling a 6-sided die, I could get a 1, a 2, a 3, a 4, a 5, or a 6. So the probability of rolling a 5, which we'll notate as P of 5, so P parentheses 5. So in this sample, how many times could an event occur of rolling a 5? Well, 1 time out of 6 total outcomes. So the number of ways that a 5 can happen in the sample space is 1 out of 6. What is the probability of rolling a number less than 5 with a 6-sided die? So the probability of getting a number that is less than 5, okay, well, how many different ways is there possible for a number to show up that is less than 5? Well, that would be 1, 2, 3, or 4. So that's 4 ways that we could roll a number that's less than 5 out of a total of 6 ways. If we're writing this as a fraction, that can reduce to 2 over 3. What is the probability of rolling a 3 or a 5 with a 6-sided die? So the probability of rolling a 3 or a 5 with a 6-sided die, well, let's see. There's 2 different ways that I could roll a 3 or a 5 by rolling a 3 or a 5. So there's 2 ways that that could occur out of a total of 6, which is 1/3. What is the probability of rolling a 7 with a fair-sided die? So the probability of rolling a 7 is going to be 0 because it's not possible at all. If we have a 6-sided die, it's 1 through 6. All right, let's look at another example. A bag contains 6 red Skittles, 9 yellow Skittles, and 2 green Skittles. You reach into the bag without looking to pick a single Skittle to eat. What is the probability of picking a red Skittle from the bag? So the probability of picking a red Skittle, so how many different ways are there to pick a red? Well, there's 6. Out of how many total? Total, there's 6 plus 9 plus 2, which is 17 Skittles to choose from. So there's 6 different ways out of those 17 Skittles. There's 6 different ones that I could pick that are red out of a total of 17. What is the probability of picking a red or a green Skittle? So the probability of picking a red or a green Skittle, so let's see, how many different ways can I pick a red Skittle or a green Skittle? So that would be 8 ways, 6 ways to pick a red, 2 ways to pick a green, so 8 ways total out of a total of 17 Skittles. What is the probability of picking a Skittle that is not green? So the probability of picking a Skittle that is not green, so let's see, how many Skittles are not green? Well, there are 6 red and 9 yellow, and that's it, that are not green. So there's a total of 15 Skittles that are not green out of 17. Now let's look at the complement. The complement of an event is its opposite. For example, if A is picking a green Skittle from the last example, then the complement, which we denote as A with the superscript of C, so A to the C power is kind of what it looks like, is the event of not picking a green. To find the probability of the complement, you can use the following formula. The probability of the complement is the same thing as 1 minus the probability of the event occurring. So for this probability that you're not green, that could be written the same way as 1 minus the probability of the complement of being not green, which is being green, which is 1 minus, there's 2 greens out of 17, which is 15 out of 17, what I found earlier. So the complement rule is actually extremely helpful, especially when we're dealing with larger data. Suppose the probability of winning a door prize at a charity event is 26%. What is the probability that you won't win the door prize? So the probability that you won't win a door prize, So let's see, they told us the probability that you would win. So we're looking for the complement. So 1 minus the complement of not winning is winning, which gives us 1 minus 26%, because the probability of winning was 26%, which is 74%. Let's look at another example. An ice cream truck operator keeps track of the number of ice cream delights sold. She finds that out of 80 ice creams sold one day, she sells 26 sherbet bars, 48 fudge bars, and 6 Rocky Road bars. Using the information gathered, calculate the following. A, what is the probability that an ice cream delight sold the next day is a fudge bar, a Rocky Road or fudge bar, and not a fudge bar? Okay, so let's first start with a fudge bar. So the probability that it is a fudge bar. So how many of the bars were fudge bars that she sold? 48 out of a total of 80 ice creams, which gives us 0.6. What is the probability that it's a Rocky Road or a fudge bar? So the probability that it's Rocky Road or a fudge bar. So let's see. There's 48 fudge bars and 6 Rocky Roads, so 48 plus 6 divided by a total of 80 ice cream bars. So that leaves me with 54 out of 80, which is about 0.68. What is the probability that it is, not a fudge bar? So the probability that it's not a fudge bar, I can find by actually using the complement rule. So that's going to be the same thing as the probability that it is a fudge bar, which I already found. So that's going to equal 1 minus 0.6, which is 0.4. Are the probabilities you calculated in this problem theoretical or empirical? So in this case, this was based on observations. She kept track of what she sold. So because of that, this is known as an empirical.